Now, ladies and gentlemen, the next subject in the presentation will be the future of HPC is looking a lot like AI ML. And for that, ladies and gentlemen, I'd like to introduce on stage our next presenter, Dr. Barry Boulding. He's the GTM lead for HPC, Autonomous and Quantum Computing, Amazon Web Services. Right up here on stage already. Let's give him a round of applause, shall we?
Thank you so much, and it's so good to be here as everyone in person, and we're starting to get back to where we can shake hands and have these conversations. Today I'd like to spend some time not so much talking about technologies as talking about innovation, and innovation in software and innovation in applications, and how these can be applied in hybrid and cloud environments. I really am excited over the last 3 to 4 years that we've seen a really amazing change in the way algorithms are being looked at. The growth of machine learning as a fundamental algorithm for high-performance computing is beginning to pervade a number of application areas, and I want to give a flavor for that. So I'll spend about 5 minutes talking about the underlying technologies, and then I'll give some examples of how machine learning and HPC are converging to solve immense problems. Today, we've heard a lot about some really fantastic applications for high-performance computing, the SKA square kilometer array applications. What's common about many of these applications is they require an immense amount of computational capacity, data capacity, and they require a workflow that moves data and processes data using different technologies. I thought it was really nice for the square kilometer array example. Sarah Pierce talked about the need for GPUs, CPUs, transcoding devices, a network that was global in scope. And the thing is, that type of broad application isn't just for solving a square kilometer array size problems, and you don't need $1 billion or $10 billion to have access to all those technologies and solve such a complex workflow. So today in the cloud, because we provide an array of technologies and technologies that customers want to work between their on-premise systems and the cloud, we're able to solve every type of high-performance computing application that are conventionally known. Things like weather forecasting, reservoir simulations, computational fluid dynamics. All the classic problems can be solved. But what's really exciting is the way innovation is happening around those applications. And core to that innovation is that machine learning has made immense advances, the ability to solve deep neural networks. And now machine learning is becoming a core component of those high-performance computing applications. In the last 5 to 10 years, we've seen a move toward using cloud resources to solve these technologies. And I really want to focus today on the left-hand side of this slide, where it's talking about innovation. Because when you have access to all these different technologies, you have the ability to innovate faster. And that innovation is really what I want to focus on today, because that innovation is about technology, core technologies, but it's also about the software and how you can apply it if you have access to all the different technologies that we see. Now, core technologies, you need good storage, you need good compute, you need good networking, you need good software to orchestrate complex workflows, and you potentially need great visualization for engineers and scientists to be able to see the results that they're displaying. And AWS has all of these available to every user worldwide. And that includes key partner technologies like Intel and AMD and our own technologies where we're innovating and developing ARM-based processors or inference and training technologies. It includes acceleration technologies such as GPUs, the inferentia and trainium processors, FPGAs and transcoding devices, And as I said, when you look at something as complex as a square kilometer array, in fact, you need all of these technologies in order to solve those problems. And what cloud tries to do is make all of that available, not just to the largest researcher, but to every researcher. Core to the compute infrastructure is a little bit of an alphabet soup on AWS. We provide a large number of what we call compute instances. And these are the core basic compute infrastructure. And as I said, this includes CPUs, GPUs. I'll skip through this pretty quickly. I know we're all trying to get to lunch. And I really want to get to the example of how machine learning is applicable to this. One of the ways that we tried to enhance machine learning and large-scale HPC applications is to allow an easy deployment of a large set of resources to the scientist or engineer. And we have an infrastructure called the Ultra Cluster, where we can allow a scientist to deploy up to 4,000 GPUs, the NVIDIA A100 GPUs, in conjunction with high-performance storage and in conjunction with high-performance networking of up to 400 gigabits. All those numbers mean that we can solve some of the most complex deep neural networks for scientific applications, and that infrastructure is easily deployable at the click of a button. So essentially, a supercomputer at the disposal of the researcher with a few clicks of their mouse and a few enters of exactly what type of configuration they want. And finally, today, infrastructures need to be hybrid. And what I mean by hybrid is I mean a mix of on-premise technologies and cloud technologies. And we're seeing that many of these researchers need to have both. And we're enabling it so that you can easily move data back and forth. And we have technologies such as our engine frame hybrid HPC software that allows the administrator and the scientist to move data back and forth and submit those jobs across both the on-premise and cloud technologies. And that's important for workloads that we've seen, such as the life sciences workloads today, the SKA square kilometer array workloads. And finally, the nice thing about cloud is you have massive scale. You have the ability, if the problem grows, to solve the problem with millions of CPUs or thousands of GPUs. And we have examples of how drug designers are using up to 2 million CPUs, virtual CPUs, to solve looking for cancer vaccines and cancer antigens for proteins. We have seismic companies looking to solve very large data sets to look at the subsurface layers for reservoir modeling and seismic modeling to find oil and gas deposits. And we have companies like Descartes Labs that are looking at sustainability of forests using global information systems and satellite systems in order to process data. All of those are applications that need very large scale. Now, how does the convergence of HPC and machine learning come into play? And this is really, I want to give an example because this is a set of algorithms that have evolved over the last 4 years or so. We started seeing publications in around 2018, 2017, 2018, 2019 that were associated with what's called physics-informed neural networks. And these are really have the potential to greatly enhance innovation for conventional HPC. Now, again, I'll go quickly here. Physics-informed machine learning, or HPC, is really about extracting data from full-scale simulations and then seeing if you can accelerate that data by making approximation to the physics in order to solve problems more quickly with an approximation and be able to predict what that's going to do in the physics models. By doing this, you can really have an AI infrastructure coupled with your conventional physics architecture that's solving a set of partial differential equations. And I'm going to show you a very simple example of this. So you may have a set of theoretical or experimental data. In this case, I'm taking the simplest of models from Physics 101 classes, which is a damped harmonic oscillator. And you may have a set of data, and at first, if you try to fit that data to a neural network, it's very difficult. You can't really fit a complex set of physics data to just a set of deep neural nets and the coefficients involved in that. And the problem is the loss function, the function that you parameterize and try to optimize on, is really not built for physics. It's just built as a neural network. It has no information about the physics world. Now, if you instead begin to incorporate actual physics equations, whether in this case it's a simple damped harmonic oscillator equation into the loss functions for the neural net, you can actually begin to optimize and fit the physical data more accurately. Now, so basically, you're taking a deep neural net, you're fitting it to a physics-informed model, and you're getting a set of results. Now, what does that gain you? So okay, we can do that, that's cool. The real question is, can you take a complex physics model, like a turbulent flow model around, let's say, air flowing through a jet aircraft engine, or air flowing over a race car, or air flowing over a wing based upon a wingtip design in a Boeing or Airbus aircraft, and can you accelerate how quickly you can solve that physics model? A full computational fluid dynamics model for, let's say, a jet aircraft engine could typically take days or even weeks to solve the full physics model. Or you might need a supercomputer, as we heard from Riken. Basically, running that full physics model is very time consuming. And if you're an engineer trying to design the bumper of a car, or the wingtip design, or change the turbine blades in a jet aircraft engine, you don't want to sit around for 2 weeks to see if that change in design reflects positively or negatively on the actual engineering. And so this is where a physics-informed neural network can quickly give you approximate designs. So what I'm actually saying here is you can decrease the amount of computer time you need and get to designs more quickly. And again, for the sake of time, let's say that you had a couple of key objectives. It could be a coefficient of friction for a car. If you have that design parameter, you can run through tens of thousands of designs in a few hours, pick the designs that seem to have the best parameters or the best results, and then go back and run a full physics simulation. So this type of neural network enhanced model, because it's an approximation, is not going to be the exact model, but if you can get to it in minutes, and you can change the design again, and you do another set of designs, and then you can do 10,000 designs an hour, you can go through and really begin to look at new architectures you never would have considered. You can spread and expand the design space in which you're looking, because you're no longer constrained by solving a full physics model. And then you can always go back and check and double check before you go to actual manufacture. And that's really the power of using physics-informed neural networks. And now, how does that relate to cloud? Well, in the cloud, you have all of the tools you need for these types of complex workloads. You have the GPUs that you need to solve neural network problems. You have the CPUs that you need to solve the partial differential equations. You have the data sets and the large S3 storage capacity. You have fast file systems such as Lustre to enable you to pull data in and out as you're doing the full physics simulations. You have FPGAs and transcoders. You have every one of these types of technologies at your disposal. And so you're no longer constrained in the workflow by having to just solve one problem one way. You can solve it multiple ways, you can get to that solution more quickly, and you can speed up the power and capability of your innovation. There are numerous examples like this at the convergence of machine learning and HPC. And I do believe, one of the reasons I work at AWS is I believe cloud empowers people to begin to look at all these different applications. And I'll give you a couple of more before we break for lunch. In the area of predictive modeling for digital twins, very similar situation. And in fact, you can use these physics-informed models to do some of the quick solutions around digital twins, whether that's a physical digital twin of a jet aircraft turbine, or even a living digital twin of a patient in a hospital. Those types of informed neural network models could be applicable. You could be able to apply those and begin to see solutions in the predictive modeling of digital twins. And so that autonomous computing area is really an area that's going to explode in terms of these complex models at the convergence of HPC and machine learning. Another area is in autonomous vehicles, where you have a complex workflow that includes training models. You need to train a model to recognize a pedestrian crossing a street, to recognize a stop sign. That type of trained model needs to be rerun occasionally based upon the data you're getting back from a fleet of cars. And at the same time, you need to test that machine learning model. And to do that, you have to run driving simulations, millions of miles of driving simulations, before you can begin to have confidence that those machine learning trained models are properly recognizing the pedestrian crossing the street, and that you haven't somehow introduced an anomaly when you've retrained the data set. So these types of fully autonomous driving models are going to involve a convergence of conventional high-performance computing to do the driving simulations with machine learning in order to do the training and inference. Another area is in the area of imaging. Cryo-electron microscopy and the technologies like that are beginning to involve looking at how complex molecules and proteins, enzymes are designed, and being able to run those through a workflow where you can quickly and automatically get to a full-featured and accurate design for that complex structure. And then you want to do docking of drug molecules into those proteins or enzymes. And so this complex drug discovery workflow is ripe for high-performance computing in combination with machine learning. So really, these types of digital twins, machine learning models, where we're connecting a physical system, a physics model, with a simulation, these physics-informed models are really going to be critical to us being able to solve the problems of the future. And I just wanted to give that inspiration. AWS is inspired by this type of software innovation, application innovation. And we really do see that it's going to take a deep collaboration between technology providers creating new accelerators, data innovators giving us better and faster access to data, and complex and innovative software that's able to run on top of cloud and on-premise infrastructures to be able to solve these problems. And I really just wanted to make sure that we understood that this type of convergence of machine learning and HPC is really going to incorporate all of these technological innovations and software innovations. It's going to involve, every one of the mathematical domains that the scientists and engineers in this room are driving. And again, I just want to make sure that you guys are aware of this. Today, we have customers in the aerospace industry that are putting these methodologies into practice. We have customers in the auto industry that are putting these methodologies into practice. We have an auto manufacturer that was able to speed up their innovation on car design using this physics-informed model by a factor of 3,000 over what it was when they were just solving the computational fluid dynamics alone. And that type of speed and innovation is going to be critical in solving these complex problems. I'll leave us with one final area, and I talked earlier about a customer of ours called Descartes Labs. And really this goes toward global sustainability. And Descartes Labs is a global geospatial insights company where they're taking satellite data and they're trying to automate the ability of interpreting that satellite data in order to provide their customers with insight. And this could be something as simple as automatically recognizing a plot of palm that had disappeared, or a plot of forest that had disappeared in the Amazon, and being able to flag that change automatically so that their customers, whether that's a government or a private entity, could understand and recognize this. It could also apply to shipping and supply chain, being able to recognize the movement of ships in the ocean and be able to understand how those satellite information and that geospatial information could be automated and automate the recognition, because the data is so complex you can't rely on the eye of an analyst to be able to recognize these types of problems. And they're using AWS to do this. And one of their customers has deforestation alerts, basically signaling that customer when they're seeing satellite information that recognizes deforestation in certain areas. And that type of innovation is really critical. They're using a combination of high-performance computing and machine learning to do that autonomous recognition of changes in the environment. So thank you for your time. I just want to acknowledge our customers and members of my team that worked on many of these projects with our customers. And I really thank you very much for your time today. And I hope we all have a great conference over the next few days.
Thank you kindly, Mr. Boulding. Thank you very much.